They both tell you the same thing, luckily. That's what you want. Okay, so now how do you know which direction this thing turns? This thing acts like a magnet. It acts like a magnet with the North Pole pointing in. I need a magnet. I happen to have one right here. Magnet, North Pole pointing in. The North Pole wants to align itself with the magnetic field. It's pointing that way, so it's going to rotate this way. This side comes out towards us. This side going away from us. Right? It's going to rotate like this so that it's aligned with our external field. What did we say earlier? We said if this was a loop of wire, this side has a force out, this side has a force in. It's going to rotate this way. They both tell us the same thing. But kind of pick which one makes the most sense to you. Did I answer your question? Okay. All right, let's take a little break, and then we'll start the next chapter. Let's start the next chapter. And this is where things start to get really interesting. Fun stuff ahead. So the idea here is that interesting things happen when we have changing magnetic fields. Actually, it comes down to flux again, changing magnetic flux through a loop of wire. So just a quick reminder on flux, right? Remember when we first talked about it with electric fields and Gauss's law, I used the example of the river. You're trying to catch a fish. Let's pretend that, unlike a real river, the flow of water is uniform across the whole river, and you stick your fishing net in there, and if you stick your net in like that, you have zero chance of catching a fish, right? No water is penetrating the surface. If you put it in at an angle, at least you have a small chance of catching a fish. And if you put it in perpendicular, you have maximum flux, right? The maximum number of field lines penetrating the surface area. And what does it depend on? So remember, the electric flux was E times the area times the cosine of the angle between them, right? Why the cosine? Because we chose the normal to the surface. The normal and our electric field, if this, instead of this being water, if this was electric field, right, it would be pointing in this direction, and that's theta, and so here they both point in the same direction. So we get a maximum there, and over here they point 90 degrees apart, so we get 0. And it makes sense, right? The flux, the amount of, in this case it was electric field, it could be water penetrating our fishing net. The amount of flux is proportional to the flow of water, right, or the strength of the electric field. You increase the flow of water, more water is going to go through your fishing net, right? If you increase the electric field strength, more electric field lines will penetrate your surface area. If you get a bigger net, right, increase the area, more water flows through the net. Increase the area, more electric flux. And then, of course, the orientation comes into play, right? You can maximize it, minimize it through the orientation. So that makes sense. So the same is true for magnetic flux. The magnetic field, the area, cosine of the angle between them. So we get a magnet, get a loop of wire, hold the magnet next to the loop of wire, there's lots of flux, right? Lots of magnetic flux through this loop of wire, but nothing happens. And if you remember back to charges, the force on a charged particle in a magnetic field, if there was no motion, if the particle was at rest in the magnetic field, it felt no force. So the particle doesn't have to be moving. The field could be moving, right? As long as there's relative motion. It doesn't matter whether there's a magnetic field here, whether the particle is going like this, or whether the particle's at rest and the field is going like that, right? As long as there's relative motion between them, the charged particle will feel a force. And when the charged particle feels a force, it starts to move, and moving charges create currents, right? That's what a current is. So let's take a look at what happens here when we have a magnet and a loop of wire. This is a galvanometer. It measures current. It's hooked up to my wire. So all I have here is a loop of wire and something that measures current. There's no source of EMF, right? There's no battery. There's no potential that would cause charges to move. So if I take my magnet and I just put it gently here over the end, I now have lots of magnetic flux through my loop of wire, but nothing happens, right? But if I bring it in quickly and we change the amount of magnetic flux through that loop of wire, then current flows. And if I pull it out quickly, now there's lots of flux but no current. If I pull it out quickly, it flows in the opposite direction. Okay? So, lots of flux there. Nothing happens. If I bring it in, oops, got to hit the, bring it in, we get a big current flow, but it's still lots of flux, but no current flow. Take it out, it goes in the opposite direction. So it's this changing magnetic flux through that coil that causes charges to move. So one way to think of it is the force on the charges, right? We learned about force on charged particles in magnetic fields. There had to be motion. The charges had to be moving. Now I'm saying, well, the charges can just be sitting in that wire. The magnetic field can move. If the magnetic field moves, the charges feel a force. They start moving. We get current. That's one way to think of it. Another way to think of it is that the only way we get charges to move is if we have a potential difference, right? A source of EMF, a battery, something like that. So a changing magnetic flux in a loop of wire must act like a little battery, must create a potential difference, and that causes the charges to flow. They're both equivalent ways of thinking about it. The second way is nice because we can quantify it. We can use Faraday did it for us, actually. We can use Faraday's law, which I'll show you in a second, to figure out what the EMF is, what the potential difference is generated in that loop due to the changing magnetic flux. And then we can replace that with the battery of the same EMF and figure out what the current is, things like that. So let me show you an example.